It turns out that all square matrices have character, or an identity that we can discover using this equation. A x equals lambda x, which essentially means that we can find some vector and plug it into this matrix, and then all it's going to do is just scale the vector by some lambda, some number. We know that a square matrix is going to have the same dimensions, so an n by n matrix A is going to have n eigenvalues. And that would be these lambdas right here. These are the eigenvalues. However, the x's are going to be non-zero eigenvectors. So we have eigenvalues, which are going to be these lambdas, and eigenvectors, which are going to be the x's. For the first example, let's take a one-dimensional square matrix, and for the only entry, I'm going to put in 1. And so if we multiply that by some vector, we're going to see that, well, the lambda over here is just going to equal 1. And there's only going to be one of these lambdas because we only have one dimension. So that's just going to equal 1 lambda. However, for the x's, it turns out that the only rule is that it has to be non-zero. So as long as this is not equal to 0, essentially what we have is infinite x's. And I mean, it makes sense because you can plug in whatever number you want here from negative infinity to infinity except 0. And you're always going to get that same number back, just scaled by 1. Well, this operation that we did here is just a linear transformation. In fact, it was just a scaling transformation. So essentially we had this lambda, which equals 1 right here. And then we took a point, and I don't know, we're just going to take a point right here. We're just going to call it 1. And then we're going to put it through this transformation, but it's just going to scale it by 1. And so then when it comes over here, we are just going to get 1 again. And you could do this with any point, so you could do it with this point, and it'll just take you over here to the same point. And, you know, you could do this with any number from negative infinity to infinity. In the next example, we'll take a look at a 2 by 2 matrix, which I'll just go and plug in 2 entries here, 2 and 2. And then we're going to have a 2-dimensional vector. And if we go ahead and try to figure out what the lambda is here, well, we can probably guess that the lambda should equal 2. Okay, and of course, we know that we also have 2 dimensions here, so there should be 2 lambdas. We'll get to that in a second. But first, let's just realize that for the x's, again, we kind of have this 2-dimensional x in this case. But as long as this does not equal 0, then everything is good. So again, we kind of have infinite x's here. If we want to draw out this operation, let's consider we need a 2-dimensional space here because we have a 2-dimensional vector x. So let's just choose this point 1, 1. That's going to be our x vector. So we got 1, 1. We're going to send it through this matrix here. So we actually have lambda equals 2 that I'll put right here. And then we have another one, right? We're going to put another one over here. This is lambda 2. So we got lambda 1 and lambda 2. We're going to put there and there. It doesn't really matter which one you send it through though. So we're just going to go ahead and send it through this one. And then it's going to come over here and it's going to get scaled by 2. So when it reaches over here, it's going to be more like a 2, 2. And then we could do the same thing by putting another point over here. And of course, it's going to reach the same point over here, 2, 2, because both of the lambdas are the same. They have the same value. So we could say that this lambda has an algebraic multiplicity of 2, which means that we just have the value appearing twice when we solve for lambda. Let's complicate things a little. Let's go back to our 2 by 2 matrix. I'm going to change the first entry from a 2 to a 1. And so now instead of having 2 of the same lambdas here, we should notice that it'll probably give us a lambda 1 being equal to 1, and maybe a lambda 2 being equal to 2. If we set lambda equal to 1 and then simplify both sides, let's see what happens. On the left side, we're just going to get x1 and then 2x2. So I'm just going to put that right here. We have x1 and then we have 2 of the x2s here. But on the right side, if we try to solve for this, we're literally just going to get x1 and x2 on this side, right? x1 and x2 if lambda equals 1. Well, the only way that this can be possible is if x2 equals 0. So x2 in this case equals 0. Obviously x1 cannot equal 0, but it can equal anything from negative infinity to infinity. So we can sort of rewrite this on the right over here. We could say that this is really going to just be equal to x1, and then we have to have 0 down here. But this is essentially going to be the solutions for the x vector, and we have infinite solutions here. If we set lambda equal to 2 and we solve this, again, we're going to get the same thing on the left here. We're going to get x1 and then 2x2, because nothing really changed on the left side over here. But for the right side, now that lambda equals 2, we're going to get that we just scale both of these by 2. And so we have a 2 here, 2 there. This is going to be x1, x2. But the only way that this can be possible is if x1 equals 0. x1 equals 0 in this case, and then the x2 could be anything. So we can rewrite this as saying, well, it's just going to be 0 on top, and then on the bottom we could have any x2 we want. And so as you can see here, we have infinite solutions for both of these. But the solutions are slightly different depending on whether you chose lambda 1 or lambda 2. Now let's try to graph these. In the first example, for lambda equals 1, let's realize we have a free range across the x-axis. So I'll just draw the x-axis as being blue here. But on the y-axis, it can only be 0. So I'm just going to mark the y-axis as this black one here. Let's just realize that it's just going to be 0 there. So the x we can move across here. So if we want to make a transformation here, let's realize we're going to use lambda 1 equals 1. We're going to have that one right there. So clearly we can choose any point around here. I'm just going to choose this one. This is just going to be 1, 0. And then we're going to send it through to lambda equals 1. And it's just going to equal 1, 0 when we send it out over here. For the second example, lambda equals 2, let's realize we have a free-ranging y-axis. So I'll go ahead and draw the y as being blue here. But for the x's, it's only going to be 0. I'll just draw that across here as being black. So here again, if we wanted to make a transformation, let's realize that our lambda in this case is going to be equal to 2. And so now, if we start sending a point, well, we have to choose a different point. We're going to choose it over here. We're going to call this 0, 1. We're going to send that through here. On this side, it's going to end up over here as being 0, 2. So we have a different lambda value. Well, let's realize that we have an infinite amount of x's that we can plug in here and an infinite amount of y's that we can plug in here. It's almost as if we're spanning some kind of space. In fact, all the x's, the set of all the x's here that we were able to plug in, we're going to call that the eigenspace. Eigenspace, but this is the eigenspace of 1 because the lambda that we have here is simply just 1. And so over here we could say this is the eigenspace of 2 because the lambda here is 2. So the eigenspace of 1 and the eigenspace of 2, that's just going to be all the x's that we can plug in to these points right here. Let's make a note that in either one of these cases, we were dealing with a one-dimensional subspace of R2, right? Because this is a two-dimensional matrix, so we're going to have to be in R2. But in the first case, we only have a one-dimensional subspace here that we can use. And in this case, we have a one-dimensional subspace that we can use. So they kind of both build the basis for R2. In the second example here, though, because we had an algebraic multiplicity of 2, we didn't have two different eigenvalues. So we just have one eigenspace. And that one eigenspace is going to be a two-dimensional subspace of R2. Still a two-dimensional matrix, so we have R2, but you can see that the vectors here are actually two-dimensional vectors, these x vectors that we can plug in here. In these cases, they were just one-dimensional vectors. Here we have a two-dimensional vector. Clearly, if we go back to the first dimension here, we can see that it is a one-dimensional subspace, but I'm going to try to generalize this because it's a subspace of R to the n. So it just depends on what kind of matrix you're using here. It's a one-dimensional matrix, so this would be just reals. And here you have a two-dimensional matrix, so this would be R2. Now we could try to determine if some lambda that we're given is an eigenvalue of the matrix A. So we have to set up, number one, this equation that we have, which is the A times X equals lambda times the X. And this equation has non-trivial solutions. All that means is that we have to sort of rearrange this equation. Let's subtract the lambda x on the left side, and then we're going to sort of factor out the x's too. So we're going to sort of have something A minus this lambda times an identity matrix. We have to use the matrix there. Then we're going to sort of pull out the x vector here, and then we're going to set that equal to 0. So that makes sense. This matrix right here, A minus lambda I, is called the shifted matrix. Let's take a little example, which we'll use 1 and 2 here. We're going to say 1 minus lambda, and then we have a 0, and a 2 minus lambda. We're going to multiply that by our x vector. It's just going to have two dimensions, x1 and x2, and we'll set that equal to 0, 0. All we have to do is just solve for the x here and the lambda. That's actually kind of cool that we can solve for both of those variables at the same time. We're going to find that there is a non-trivial solution for the null space of A minus lambda I, which is this one. So essentially there's going to be infinite solutions to this equation, infinite x's, which is our eigenspace. And this non-trivial solution for null space of A is sort of the same thing as saying non-trivial solutions to this equation. This is all saying the same things. We know that if there is a non-trivial solution for the null space of some matrix, we know that that matrix is not invertible. Well, if the matrix is not invertible, that means that the determinant of that matrix that we just made, 1 minus lambda, 0, 0, 2 minus lambda, the determinant is equal to 0. If we try to solve this, then we're going to get some equation over here. 1 minus lambda, 2 minus lambda, minus 0 is equal to 0. This right here is called the characteristic polynomial. And when we solve for the lambdas, the eigenvalues, those are simply going to be the roots of the characteristic polynomial. Also, we know that that matrix A minus lambda I has linear dependent columns. Let's assume that this is some 3 by 3 matrix. So let's set up some sort of an A minus lambda, a B minus lambda, and then maybe a C minus lambda here. But if we want to figure out whether it's linear dependent columns, we actually have to augment sort of within itself. We're going to take that third column as being the augmented column here for the previous two. What that implies is we can make a linear combination of these two columns. We're going to have sort of column A1 here and column A2 here, and then here's the column A3 over here. But we could make a linear combination by having like a coordinate 1 and a coordinate 2 over here. So some combination of these two is going to create this third column. We have to solve for that. Here's an example of a solution to that. It'll be something like 1, 0, 0, 1. You'll have some zeros down there. This will be augmented here. We're going to have like a 0 here. Maybe there'll be like a 4 and a 3 in these particular positions here. So that's just telling you that C1 equals 4 and C2 equals 3. And so now you just plug those in there and you're going to get that 4 times the A1 column plus 3 times the A2 column. It just gives you the third column over here. So we can see that these are linear dependent columns. So to recap, the key here is that you're going to want to solve the matrix A minus lambda, B minus lambda, C minus lambda, multiply that by some x vector, x1, x2, x3, and then set this all equal to 0. If we could do this, then we're not only going to solve for all the x vectors, but we're also going to solve for all the lambdas. So we essentially solve for two variables at the same time by setting up this equation. So what we essentially have to do here is essentially fully reduce the A minus lambda I matrix here. And when we do that, we might get something like, I don't know, like a 1, 0, 0. This is augmented here, right? And then we have a 0, and then we have a 0, 0, 0, 0, 0, 0, 0, 0. We essentially just have zeros everywhere. This is entirely possible. We could just get a whole bunch of zeros after fully reducing this matrix here. But remember, we're trying to find the set of all the x's, and this is going to give us a solution for the x's. Let's set it up here. So we got x1, x2, and x3. We know that x1 is simply equal to 0. That's essentially what that first thing is telling us. But x2 is actually a free variable, and so is x3. These are actually free variables. Let's just take a note over here that we're going to have to find our pivot point right here. This is the pivot. We can see the pivot just equals 0 in that case. But for these guys, we actually have two full columns of 0. And so these guys are going to be free variables. So we could look at the answer in 3 layers, because we're sort of seeing how at the top here we have x1 is just equal to 0. And in the middle here we have x2 is equal to 1 times x2 plus 0 x3. That just makes sense. And then over here we finally have that x3 is equal to 0 times x2 plus 1 times the x3. So we've actually found the set of all x's here. And it turns out that there's 2 basis vectors here. Since this eigenvalue has 2 basis vectors, then it turns out that the eigenvalue is going to have a geometric multiplicity of 2. This is a little bit different than the algebraic multiplicity of 2, where we found that we had 2 eigenvalues being the same value. In this case, we have 2 basis vectors, which means that we just essentially have a bigger subspace. As you can see here, this would have 2 basis vectors. This only has 1 basis vector, 1 basis vector, 1 basis vector. So in fact, we can write that this particular eigenspace is a 2D eigenspace of r to the third. Now let's consider, what if lambda is equal to 0? What would that mean? It means that a times x now all of a sudden just equals 0. And so we know that this actually will have a non-trivial solution. Just like this first rule right here. Well, now that A is acting as the shifted matrix, we can essentially just say that the determinant of A is equal to 0. And we know that if that's the case, then A is not invertible. And because of that, we know that the rank of A is definitely going to be less than n. So what does it mean to be an eigenvalue? Well, let's consider this concept of stability. So let's have a matrix here filled with some information about like rates of a particular population. Population is going to be the population vector here. And so we're going to plug that into this little a times x situation here, and we're going to get a lambda times that population vector coming out on the other side. So if the lambda is greater than 1, it means that the population is going to go up the next year. If the lambda equals 1, then we have a constant population. And if the lambda is going to be less than 1, then the population is just going to go down. The idea here is that if we want a stable population, we're going to want a lambda equals 1, so we get a constant population. Now let's say we were given some x vector, and we want to know whether it's an eigenvector of our particular matrix. So let's say we have the matrix 1, 0, 0, 2, and we're given the vector 3, 2. So all we have to do is just plug that vector into the matrix and ask ourselves, well, what's the answer here? The answer is going to be 3, 4. So if we compare the vector 3, 2 with the vector 3, 4, you could see that it's not been scaled. This has not been scaled. It should have been like 6, 4. Then it would have been scaled. But instead, this is not an eigenvector because it was not scaled. We might have noticed so far that these diagonal matrices are really important because they basically just instantly reveal the eigenvalues. What's interesting is that we could take these eigenvectors and multiply them by the eigenvalues, and then we can get this equation, which says that P times D is going to be equal to A times P. So we can do a whole bunch with this equation. Let's note that we're taking the vectors times the values, and then we're going to get the matrix times the vector. The P matrix consists of the eigenvectors. So this would be x1, x2, x3. These eigenvectors will actually correspond to particular eigenvalues. So eigenvalue 1, eigenvalue 2, eigenvalue 3. That simply leads you to these 3 eigenvectors. So we can say that the columns of P are the eigenvectors of A. If we want to determine whether some random matrix A is diagonalizable, meaning we can rewrite it in this form right here, where the eigenvalues are apparent, then the eigenvectors of A must be linear independent, meaning that they must form a basis for R to the n. There's a quick shortcut to know whether we have linear independent eigenvectors. If we have unique eigenvalues, the unique lambdas, then that'll work. We don't have to do any more checking. We know that we have linear independent eigenvectors. Even without unique eigenvalues, we can still have linear independent eigenvectors. But if we don't have linear independent eigenvectors, we might have to do something like translate it into a Jordan matrix instead of a diagonal matrix. Assuming everything went smoothly, let's go ahead and form the D matrix. That's just going to be the eigenvalues. So we're just going to plug those into the matrix like this, 1, 2, 3, and put in some zeros as well. We can see how the columns of D are simply going to be the eigenvalues here. But of course, these eigenvalues, lambda equals 0 is okay. It still could be diagonalizable. If we multiply this out, let's notice that it would be something like lambda 1 times only the first entry within x1. So we got x1, 1. Then we have lambda 2 times only the second entry within x2, so x2, 2, times lambda 3 over here only times the third entry within x3. So we kind of have this little matrix here that we've formed, and we have zeros everywhere else. And this matrix right here is going to be equal to A times P. So what this means is, let's shrink this down to one dimension. We're going to have a little matrix here that's lambda 1 times some x. And that one-dimensional matrix there, just one entry, is actually just going to be equal to the matrix A times the vector x. And this is just in one dimension. The reason this is so powerful is we can take this expression and multiply it by the right on both sides by the P inverse. If we do that, this side is just going to cancel out and we're just going to get an A. And then on the other side, we have P times D times the P inverse. So let's write that P times D times the P inverse. And because we've already established that A is diagonalizable, that means that A is actually similar to D. And if that's the case, that means that the determinant of A is actually equal to the determinant of D. And what's really cool here is that now we could start to sort of square things. So we could square this A over here, and we'll make it, I don't know, we'll put it to the power of K. And then over here we can put d to the power of k. This here will also turn out to be a to the k is the determinant of a to the k. So as long as we can figure out that we have linear independent eigenvectors, we could translate A into diagonalizable matrix, and then we can use these two equations to basically calculate a to the power of k or find the determinants as well. Let's also consider the upper or lower triangular matrices. So their eigenvalues are actually going to be across their diagonals here. And then we have the ABC for the upper, or the ABC down here for the lower. But yeah, so the eigenvalues are along the diagonals. Lastly, let's consider some differential equation. Let's say that we have ax is equal to dx over dt. If that's the case, we're going to want some x as a function of t. That's going to be equal to some constant vector v times the e times a constant lambda, which is the eigenvalue, times some t. If we plug this in, we're going to get something on the left that says a times, well, let's plug in this x. It's going to be v e to the lambda t on the left, but on the right, we're essentially going to take the derivative of x, and if we do that, it's just going to be v e lambda t, and then we have to do the chain rule, so let's put the lambda in front. Let's get the lambda times the v e lambda t on the right side. Well, we can see how the e lambda t's can sort of cancel out here. So finally, all that's left is going to be a times the vector, which equals lambda times the vector.